Thanks for watching. And here is an important class of PDE methods called the energy method. And in particular, in this video, we want to show that if U solves the wave equation, so if U solves UTT equals c squared uxx, then a certain energy is conserved. Then the following energy is conserved. Energy is conserved. Namely, in this case, we define the energy E of t, so Et wants to go home, as 1/2 times the integral from minus infinity to infinity of ut squared plus c squared ux squared dx. And this has a really nice physical interpretation because this part of the energy is like 1/2 mv squared, which is called the kinetic energy. And this part is what's called the potential energy. And so what we're showing here is that if you take the kinetic energy and you add it to the potential energy, then the total energy is conserved, which is already cool physically. But I do want to mention another application that we'll do in the next video is to use this to prove uniqueness of solutions to the wave equation. All right, let's see how we can do this. Now, the first method, which we won't do, would be the calculus way, meaning that given your energy, you just need to show that the derivative of the energy is 0. Now, why won't we do this? Because it's kind of bad in the sense that you need to know what the energy is beforehand. So problem, need to know what E of t is. Of course, here we can do it from physical considerations, but in general, for general PDE, it's not obvious what the energy is. Instead, what we'll do is to use what is called the energy method. Which is, we will start from the basics, just from the PDE, and build up to the energy. How? By multiplying by a clever function and integrating by parts. You'll see. So, step 1. So start with our PDE, so UTT equals c squared uxx. And the trick is to multiply the PDE by a helper function which in this case will be ut. And at the end, I'll tell you sort of how to find the function. And by the way, if you know a little bit of ODEs, this trick should remind you a little bit of integrating factors. Because integrating factors is the same thing. You multiply your ODE by a clever function to simplify it. Okay, now let's do that. Okay, so we have UTT equals c squared uxx. Now, we multiply this by our helper function. So UTT ut equals c squared uxx ut. And remember, we want to build up to our energy. So now what we do, we integrate this with respect to x from minus infinity to infinity. So integral minus infinity to infinity ut dx equals integral from minus infinity to infinity c squared uxx ut dx. And you see now we have two terms, the left-hand side and the right-hand side. So the left integral, we call this a, and that is c squared, and the right integral, we call it b. So now we get a equals c squared b, and what we want to do is simply study a to simplify this, study b to simplify this, and then you will see our energy method or conservation of energy will just slip out like bread and butter. Okay, so let's do this. Let's study A now. Okay, so step 2. So study of A, which I like to remind you is the integral from minus infinity to infinity of utt times ut dx. And what's the idea? The idea is to write this as a single t derivative. So idea, write utt times ut as something with respect to t. Because the idea is then we'll be able to take the t derivative out, and you will see soon why this is so useful. And for this, I would like to remind you of a little calculus fact. Namely, if you take a function y of t, so if you want for any y of t, we have the following. If you take y of t and multiply by its derivative, this whole thing can be written as a derivative. So it's just d over dt 1/2 y of t squared. And the proof of this is just a chain rule. If you take the right-hand side and you differentiate this, you get 1/2 times 2y of t times y prime, which simplifies to this. And notice this is perfect because utt is precisely the derivative of ut. So we can really write this as one derivative. So here, while we have ut, that is ut t times ut. So if this is y of t, this is y prime of t. And the point is now, you can write this as one derivative, d over dt, and then 1/2 ut squared. And we can use this simplification to now simplify our integral. So once again, what is A? A was, I believe, the integral from minus infinity to infinity of utt times ut dx. But now we have our simplification. So we wrote this as integral from minus infinity to infinity of d over dt of 1/2 ut squared dx. And now notice the 1/2 comes out intuitively. T is constant with respect to x, so that derivative comes out as well. And to be rigorous, you can use dominated convergence theorem. And so in the end, this simplifies to d over dt of 1/2 times the integral from minus infinity to infinity of ut squared dx. at this point, I want to invite you to go back to the beginning of the video and notice this is precisely the first part of our energy, which again is good because I told you, what if you don't know what the energy is? This helps you rederive it. So I believe step 3. So B in this case is the integral from minus infinity to infinity uxx and then ut dx. And now once again you will see why in a second, but what would be nice is to put one of those x derivatives on the right hand side. And so notice we have the product of two functions. We want to put the derivative on the other side. So this is the perfect time to use integration by parts. So I want to remind you, what does integration by parts say? IBP. It says that the integral of u dv is uv minus integral of v du. Okay, so now what does b become? So b, remember, is the integral from minus infinity to infinity of uxx ut dx. Now, we can use this ut as our u and uxx as our dv. And technically dv is uxx dx. And what does this become? Well, now it's uv. So in other words, a ut times ux from x from minus infinity to infinity. So that's kind of our uv. And then minus v du, so minus integral of minus infinity to infinity of ux and then utx dx. So that's v du. Now, just a little simplifying assumption, which also makes sense physically. Just like for our Fourier transforms, we will assume that our waves are 0 or at plus or minus infinity. So in particular, just by assumption, we will assume that ut goes to 0 and ux goes to 0 at plus minus infinity. So just to illustrate, if we have a wave like this, let's say that splits up into 2, for every time if x is plus infinity, that wave is 0, and so is its velocity. If x is minus infinity, that wave is also 0. Because remember, t is fixed here. And using that, we can simplify b. And so in this case, b just becomes minus the integral from minus infinity to infinity of, and I'll write it in a more suggestive way, so uxt times ux dx. And the reason I wrote it in this way is because once again, we can use the calculus fact from the previous step to write this as one derivative. Because note, well, uxt and then times ux, that is once again like y prime of t times y of t, and that becomes d over dt and then 1/2 ux squared, because that is the 1/2 y of t squared. And using that, we can now simplify our integral. And so b now becomes minus integral from minus infinity to infinity of d over dt and then 1/2 ux squared dx. And just like before, we can take out the d over dt and the 1/2. So what we're left with is d over dt and then minus 1/2 integral from minus infinity to infinity of ux squared dx. And once again, I would like you to pause for a second and notice that this term also appeared in our energy. So that was the second part of the energy that we needed, kind of like a second amulet. And now we want to put both amulets together and see what amazing weapon we get. So now last step is the grand finale. Because what did we have? So A was c squared b. Now A we were able to write as a t derivative. In other words, we have d over dt 1/2 integral from minus infinity to infinity of ut squared dx. And same thing for b. So that was c squared and then d over dt of minus 1/2 integral from minus infinity to infinity of ux squared dx. And the cool thing is, now we can put everything under one t derivative. So what we get, d over dt of 1/2 integral from minus infinity to infinity of ut squared, and then plus c squared ux squared dx. This whole thing, or this whole derivative, becomes 0. And you see, oh, we have our energy here, because if you let e of t to be whatever that integral is, then we have shown that the derivative of e is in fact 0. So e prime of t is 0, and therefore, finally we have that e is constant. You see, and this is extremely cool because at no point did we guess what the energy was. We literally started with the PDE and eventually found the energy. Now, I just want to give you a couple of remarks. So, first of all, the thing that confuses the students the most, the question is, what is the energy? The problem is, the energy depends on what PDE you use. So, for the wave equation, there is a certain energy. For the heat equation, there's another energy. So here, energy is loosely defined. It's whatever you get after integrating by parts. So some quantity that is useful for the PDE. Now, another question that I always get is, what do you multiply your PDE with? So in this course, I want to give you a little rule of thumb. So rule of, so kind of turkey. If you see an equation of the form ut equals to blah, usually multiply by u. That we'll see with the heat equation. And today for the wave equation, utt equals something, usually multiply by ut. The reason I'm saying usually is because it's not always true. Sometimes you can get interesting information if you multiply this first PDE by ut. But unless otherwise specified on the exams, for instance, usually you just multiply by one of those two things. However, I do want to tell you, figuring out what to multiply UPDE with in research is really an art. So, for example, for my PhD thesis, literally for a year, I was trying to figure out what to multiply my PDE with, and once I figured out, that's when I could write my thesis. Just to show you how delicate this problem really is. Really figuring out the correct function to multiply this by. And finally, one more thing I want to mention is there are two very cool applications of this. Well, first of all, it's kind of cool to know that for the wave equation, the total energy is constant. For the wave. For the heat, we'll see a different phenomenon happens. That's part of the next videos. And also, the next video, actually, I will show you how to use this to show uniqueness of solutions of the wave equation. And that will be the part of the next video. Alright, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.